We're right on the 30-minute spot, so the floor is yours.
Thank you for the presentation.
Thank you, Ishan.
I don't know, maybe I will just 1 second, please. Okay, 1 second. Can you see my whole screen? Okay.
Yes.
Yeah, so I wanted to discuss this very exciting article called The Dissociation Between Artificial Intelligence from the Artificial Consciousness. Yeah, like for this introduction, I saw some analogy between the examples in art, and in this case in movie, like Ghost in the Shell, trying to answer if there any like soul or ghost in the machine. And it's also related to the introduction about the kind of emergence of so-called artificial general intelligence, and also like the functional equivalence of what we do as a human, but replicated by machine, by artificial intelligence. And those are they also conscious in this case if they reproduce what we all do and sometimes even outperform us? And yeah, it also has a lot of like implication, practical, how to interact, about the ethics of AI and so on. And even like from the initial kind of introduction of some tests of artificial intelligence, such as Imitation Game by Alan Turing, he explicitly dissociated the intelligence and the consciousness in his work. And there is some common assumptions about functionalism that by replicating cognitive function, we could also say that it's sufficient for consciousness. And then this paper, Integrated Information Theory, challenges this assumption. And interesting that this is also very important societal kind of agenda. And for example, recently I found this article in a Swedish journal saying that Nobel Prize winner Jeffrey Hinton suggests that AI is already conscious. And then I found also in some international sources as well, like saying that Godfather of AI, like saying that AI is already conscious. And for me, it was very interesting, and I'm curious and want to explore this area even more. That's why I selected this article as well. So, so to answer those questions, we need to kind of have a proper theory that could say what is sufficient for any system to have similar experience as we have. And in case of IIT, it starts from the phenomenology, from the consciousness, from experience itself, but not from the neural activity patterns or some cognitive function as a usual approach. Here is just an overview from the Integrated Information Theory wiki, showing how integrated information theory kind of workflow could be perceived, that you start from phenomenology, from experience, and then you formulate phenomenal properties in physical terms, and then investigate the integrated information of a given system, and then you try to kind of account for this in your experience. And then you could also use IIT to validate your prediction. You could say about specific anatomical location that's important for consciousness. And you could, for example, use some perturbational approaches, such as perturbational complexity index, that are measured by the implementation of TMS pulses and reading of the neural activity responses through EEG. And then all this knowledge you could also use to extrapolate to other kind of systems and conditions. For example, if it's unconscious patients, if it's embryo, it's of other species, and also importantly for this specific article about the computers, robots, and artificial intelligence. Yeah, so IT starts from the axioms, and the zero one is the existence. It's that experience exists, that there is something, and then its intrinsicality is that this experience is it exists for yourself. And there is a kind of specific that this is like special, so information, and that it's unitary. So you have one in a normal condition, you have just one experience, but then if you have some lesions, it could be different. For example, you could experience two consciousness from the corpus callosum lesions, for example, and it's also interesting cases to apply this IT predictions. And exclusion is this is definite. In this is yeah, it's specific, and then composition that it's structured in a specific way.
Igori,
Yeah,
can I stop you just a second?
yeah,
When you discussed integration and you said that in under normal condition experience is unitary, right? That I would say is not correct because according for IIT, experience is always unitary, and from the subjective point of view, it it's even hard to imagine what would it mean to have an experience that is not unitary as a subject.
yeah,
What can happen is that because you said, for example, for a callosotomy, you have then two hemisphere which are both independently conscious, but in that case, their own experience is also unitary,
yeah, yeah,
even though there are
yeah.
interesting.
Yeah,
Just to
thank you for clarification.
no,
Yeah,
no.
I meant this as well. Like, yeah.
Yeah.
Uh, And yeah, it's hard to imagine, but yeah, according to this notion, yeah, thanks. And then there are some key concepts in integrated information theory, like complex. It's a system. It's a set of kind of nodes that fulfill the postulates, and then integrated information yeah, it's showing how this system builds the yeah, like the one entity, but not reduced to smaller one, and a high fee or high integrated information suggests the richness of your conscious experience. Then there is a cause effect structure. It's a yeah. It's kind of yeah, a little bit hard to explain this all new concepts, but it's kind of yeah, it's kind of unfolded all cause and effects within this system. And yeah, how, for example, this neuron could potentially cause some changes in each other. Yeah, and the core idea is that consciousness it's about kind of what the intrinsic causal structure of the system, but not what is just about the function, what it does, but actually about some also intrinsic property of this system to integrate information. And IT has also like explanatory power to also explain why, for example, some why some cortical regions are more important for consciousness. For example, if you damage some posterior regions, you would probably lose consciousness. But on the contrary, if you remove the cerebellum, you could still be conscious. And the difference between those two architectures is that in cerebellum it's kind of parallel modules, but in the posterior cerebral cortex it's kind of pyramids of grids. And then we see that those architectures support different cause-effect structures. And then also like IT also
Right. Maybe if you can just summarize the main argument of the paper, because I am afraid that if you try to go through all of IIT, we're gonna need a couple of days at least. If it's okay, because I see.
uh, yeah, so scientific support that based on IT we could predict we could create tools that could be used clinically. For example, PCI that recently mentioned in clinical guidelines. And yeah, it's a PCI again that measure with TMS and AG, and you see how brain integrates this stimulus, and this could help you to dissociate between different conscious states. For example, in this case, it's wake and sleep, for example, and you see it's a different patterns. And yeah, one chart is one wiki where you can find all the information. I'm working on this to show. This is one article that was mentioned in the paper. So and here is a software and data sets available. So you could really play around with it. And in this article, the goal was to demonstrate that functional equivalence of the system does not phenomenal equivalence. And we see that they simulate a specific target system. It's a set of nodes, PQRS in this case. It's a 4 nodes. And they defined that they are fully connected and also with self-connections. And even this kind of simple system could give like 13 distinctions and yeah, thousands of relations and also high phi. And the systems that trying to simulate it's a 117 unit digital computer. It's kind of yeah, usual CPU GPU kind, and with yeah, key components like clock, memory, register, and so on. Like also a little bit modular. That's why I wanted to explain a little bit about the modularity of the cortex. Then I will highlight a little bit the analogy between the yeah, the architecture of the cerebellum and the architecture of this computer simulants. And then this computer could perfectly simulate the behavior of this complex. And here, as I already described, it's a system of 4 nodes. They could be on and off, and they are fully connected with connection to itself. And also, it's in the picture A. In the picture B, you see the transition between states. So it's all these nodes in 16 conditions, and you see, for example, that the top row represent they are all inactive, and it will lead in the next state that they are all inactive. And in similar fashion, you see this transition of states. It's a so-called true stable. And then in C, you see the transition probability matrix. So in this case, it shows how represents the state transition probability in this specific system, in this all these combinations of states represented. And in the case of computer, we see that it's a little bit different kind of notion that to support the simulation, you need a little bit different kind of substrate to achieve like a functional equivalence, like simulate this. In this case, you would need this kind of complex, CPU-like architecture. And in this key result that they showed that they showed the dissociation between like function and cognition and consciousness. Sorry, that the computer. Despite like simulating the system, showed low integrated information, and it was like fragmented, and the also different finding the kind of graining, trying to create macro units from this individual neurons also didn't have no like feedback connection as well. So like summarizing these findings, that we can say that in this case also it's a similar picture, but instead of cerebellum now we have this representation of the architecture that was used in this publication. And here we see that potential kind of dissociation between consciousness and intelligence, that some like organisms, like organoids, could be very conscious, have some experience, but they are have low intelligence. So there's this like clear dissociation, and also it opens floor to here they just explained the thought experiment when they replicated the consciousness with kind of integrated chips, and also with in another case with unintegrated silicon chips. And in this case they explain how kind of interpret those results in a specific kind of use case scenario. And another point for me especially was interesting because it's related. Maybe it's kind of, I will slowly transit to discussion if it's okay. Like they also, because the final, they think the prospect on the future on how to test this the same approach but for a different architecture. In this case, they consider the neuromorphic hardware, and for me especially interesting the brain scales to neuromorphic computing. It's an analog system that allows the emulation of neuron instead of like only allowing to simulate. So it's a kind of physical analog neurons. It's it has like a peculiar architecture. I'll not go into detail, but it's different from the architecture from the paper and from CPU. And I just tried some toy examples also to emulate on a neuromorphic hardware to create this transition probability matrix. It's still like a kind of ongoing project, and I wanted to kind of develop it more like during the second week of the school. I think it's a kind of great opportunity. Yeah, I think it was all for me. Thanks.
Thank you very much. And this is very interesting. I recently applied for a grant based on the philosophical implication of IIT frameworks for artificial intelligence. So I'm particularly interested on this discussion about neuromorphic computers. So I hope this is something we can really discuss more in details when we are at the summer school. But
Mhm.
let's see if there is anyone who has questions or suggestion or observation.
I have a few. Well, I have one question, and if you don't want to, it's okay. I mean, totally okay. But you had many slides with lots of interesting information, and I wasn't screenshotting. Can you share the slides?
Yeah, absolutely.
Yeah, that would be
Yeah.
nice. So about neuromorphic computers, there is something about the brain which is it's a huge stochastic machine. So although openings and closings of ion channels are influenced by input from other neurons, they are basically random. And deep down, what causes this is thermal noise or even quantum noise coming from down there in the particle world. And somehow I've got this, due to my physics background, I have this impression that this randomness is a part of the story. And so these neuromorphic computers, they're analog, but are they random at all? Are they stochastic, or they are essentially deterministic? This has nothing to do with IIT, in fact. I mean, I have
Yeah.
some questions, sorry, but
Yeah, no, I tried to have some thought about it. Like, I'm also like just exploring the system, so a lot for me to understand, and like in the context of IT and general on how you actually how these networks are even like mapped on this architecture and so on, and what are the rules and what are different parameters on how you can manipulate the hardware and so on. So I experimented, for example, with some like spikes. And then I used a similar approach with the Boolean operators, trying to do transition from states based on this also rules as they use in the article. So yeah, I want to investigate this a little bit deeper to understand, but not clear yet. I'm planning to really before we start the school. I wanted to have like a little bit deeper understanding into the architecture itself and what in what way you can manipulate it or rewire. Here is there is also possibility for like it's a you could one thing you could as far as I know you could simulate like faster than real time, so it's a like accelerated simulation. And also you could have even like structural plasticity in this chip. And here is the wiring is exactly represented um, integrate and firing neurons like ADX, adaptive exponential version of it. So and then they have some like synaptic matrices that connect those neurons, but also the wafer itself, like the single chips, also could be united in more network with some kind of extension. So yeah, it's a really I think interesting field of research and innovation in this. So yeah, I'm really happy to discuss it here. And if you have any nice suggestions or like comments on how to approach it, because I think it's very crucial to trying to understand this kind of biology assumptions that we kind of may lose through this emulation.
maybe Francesco, do you allow me? I mean, if anybody wants
I
to.
think so. I'm not qualified to reply about neuromorphic computer, but as if I understood your question, I think that of course, like as far as I understand, but I think it's neuromorphic computers are not even comparable to a biological brain in terms of complexity and everything. But as far as I understand, self-organization does play a big role, which I think was what your question was hinting at, right?
Well, I was more worried about the stochasticity, that it seems to be, it's like the fuel of our brains is noise in a way. And and this could play a role. There's even a paper in quantum mechanics called the free will theorem by Conway and Cohen, which is a funny thing. But I mean, this is, we don't have time for this. I think that's why we need the summer school, isn't it?
Yeah. But maybe one comment. But maybe one comment about the noise. I read some interesting paper saying that if you connect neurons in a like simulated neurons in a specific kind of architecture, let's say small world architecture, and kind of simulate this network, and while they connected in a small world architecture, they could both kind of produce the scale-free activity, like 1/f noise of their signal, but also scale-free and which are supported by small world architecture of this brain. I think it's also true for our brain. And I currently investigate this kind of 1/f part of the signal, which is thought to be noise, but now it seems to be representing the interrelation between excitation and inhibition. So you could infer from the kind of from this FOOF models fit like 1/f, and you could infer the ratio between excitation and inhibition. And this is, for example, this ratio could be adjusted, for example, in this network. So potentially we could create models that could also support the small world architecture. I played with some different architecture, so I tried to also simulate them, like emulate them in a small world architecture and in a random network and in a like lattice-like network, fully connected. So
Igori,
a lot of
let's see if,
exploration. Yeah.
sorry, but we are almost over time, and let's see if also Ishan and Luis want to make comment or ask question or in general. Also because we are diverging a little bit from the original paper, so if you have any.
I think it's a future direction of this kind of paper, and it's
Yeah.
just kind of or something like that.
Yeah, no, I agree. Of course, it's as I said, I'm personally interested, and I think it's definitely fit, but I don't know if
Maybe
Ishan.
a comment about the actual paper. I found it very, very interesting because I mean the difficulty about IIT, which makes it very different from something like global neural workspace theory, is that it proposes a model of phenomenology, mathematical model of that, and then how do you directly test it? Well, it has to be indirect, like the slides that Igori was presenting. So there will be phenomena which can be more or less explained in terms of this, and these are indirect indications that it's right. It's a bit of a mathematical approach that it reminds me of mathematical physics, which is an area where you might not be doing physics, something testable. You're not doing pure mathematics either, but you're doing something which can eventually play a role. There's even string theory, which is not testable at all, and somebody told me, smirking a little, well, but it does predict gravity. Einstein equations emerge from all that stuff. Well, yeah, that's a kind of measure of success. And here you have these coarse predictions that, well, if you have enough verifications of them, then you start gaining confidence that the model is somehow correct. And assuming that it's correct, then it has a very sharp conclusion about current digital computers, which is they are philosophical zombies. And that's really important, at least because we don't want teenagers committing suicide because they trust their chatbots. So societal, a huge societal relevance. So I think this is a very serious piece of work. I mean,
I was thinking this like direction to organize the Nobel Symposium here in Stockholm dedicated to this dissociation between artificial intelligence and consciousness, and I think it would be like crucial to also to have a framework to address those questions, like testing and experimentation facility where we could have the knowledge and expertise and infrastructure to answer this question, like in a systematic manner, I would say. And thinking maybe now it's maybe it's even now too late to start this kind of ethical stuff, because as we seen in my some first slides, that like public perception and from even Nobel Prize winners, that they're already conscious. So yeah.
There are two AI personalities that exchange something on Twitter or X or whatever it's called. One of them, I can't remember his name, said, well, maybe current LLMs are already slightly conscious. And there was another guy called Murray Shanahan. He said, yes, in the same way that maybe a field of wheat is already slightly pasta. So this is the level of scientific discourse that we are seeing in this field. That's terrible. I mean,
I think there is a reason.
Sorry?
Please.
Sorry.
Yeah, so it's also maybe like return a little bit to discussion from the first paper that about the, because they kind of see these chatbots and they talk as we are, so they perceive, okay, if they use the same language and it makes some sense, it also implies the kind of equivalent between kind of language and other like symbolic operations that we use, but in this case, maybe this gap, dissociation between language itself in reality and its physical kind of substrate, the territory and the map relation. This analogy that I tried to use to describe my thoughts about the first paper and how we can probably like deal with it. I don't know.
Yeah, I agree. I think we actually wrote a paper in 2021, which I think is one of the reading for the summer school. What we call the fallacy of misplaced objectivity, which is this fundamental shift from phenomenal experience as the explanatory target of consciousness to its more tangible or manifest proxies and correlates, such as the functional one. And I think this was this is exactly what happened. Like because we have now this LLM that can reproduce certain function like language quite well, actually. There is this at least in the at level of common perception, like this misalignment that well, if they can do as conscious as we, then they must also be as conscious as we are. And I think this is a crucial fallacy. And unfortunately, I think this fallacy, this has been the for a huge part of the field, this has been the one of the guiding principles so far when it came to the scientific investigation of consciousness.
Is it somehow related to some kind of fundamental displacement that Giulio Tononi sometimes refer to? Is it any relation between this misplaced stuff and
Yeah. We like Giulio is like an author of that paper, so yeah. I'm pretty sure is what he's referring to. So, all right.
Is there time for a last question?
Yeah, a very quick one for sure. But just let me last check if Ishan or Luis want to say something.
Yeah. of course.
Been suspiciously silent for the second paper. So please, let's give everyone a chance to. It's good.
I mean, I don't really have anything to add. I did read the paper when it came out, and I thought it was a nice way to push back against this thing. But I mean, personally, I think people are rushing too much into, making big claims about AI. So I think it's a useful paper to remind us that there are causally structural relationships that you can't implement in a computer, for sure. I mean, I think it is a very crucial point. And I mean, the reason I'm not saying too much is because, like, in the lab over the last 5 months, Anil's been writing stuff on this a lot. So it's just like there's lots that's been said, and I don't think I have anything to add to that.
Thank you very much.
Yeah, and same
And-
for me. I don't have anything too substantive to add. You just connected what was exposed at the beginning of Igori's presentation, that it's the confusion that there exists between recognizing what's consciousness and what's intelligence. And I think we're going to keep on seeing these kind of statements and arguments that, yeah, AGI is coming soon or it's already here, because there's just this semantic confusion between what's what. And just one thing, what I particularly like about this paper is that it says demonstration of how, a functionally system equal to that it's equal to the one that it's phenomenologically showing something. It's not actually capable of doing that. But what I especially liked is that it also gives way into how this could escalate to more complex systems. I didn't read the supplementary material because it was supposed to be for a study for 2 hours, but that would have spent more. But it goes there, and it also opens the door to that maybe in other kinds of systems like neuromorphic systems or maybe some more based on biological substrates could give way to phenomenal experience. So I particularly like that. So yeah.
Thank you so much. And a conclusion by Pedro, maybe. And sorry, by the way, for going a little bit over time, but
I mean, if you want to stop, it's okay. My question is more about IIT in general. There is something which we know is related to some subjective experience, which is brainwaves. So neurons oscillate all the time, right? And does this implicitly play a role in IIT? So, or is it totally disconnected from it?
Yeah, I might say that if I may comment from my knowledge, like that the activation itself, maybe it's not super like important in a specific, like maybe time window or something, because neurons could be silent, but they could be anyway part of the cause-effect structure, and they could play a role in the future, for example, to define the future states. And I think some experiments on meditation, like also showing that even without any, like with suppressed, maybe like I would say, EEG, like high density EEG oscillations in general, like we somehow see in the meditating subject, we see that they have a feeling of like pure presence. I think it's also one of the project by Giulia Tononi and team. I think this also maybe hints about this kind of oscillatory activity, its role, like how it be a little bit tricky to only connect it to oscillations of. But yeah, I don't know if anyone has any questions or.
It was an unfair question, not related to the paper or anything.
Yeah, but I think your answer was on point. Like so for IIT and integrated information in general is a state-dependent measure. So it's not really about activity, but configuration, so to say, at a given time. So I think, but yeah, let's finish it here. And sorry, by the way, for going a little bit over time. I hope it was funny and interesting conversation. I'll stop the recording now.